Hi, I'm Dr. Gareth Moore from RP Photonics, and welcome to this RP Fiber Power tutorial series. Today I'm going to show you how simple to use, yet powerful, our fiber simulation software is. Let's dive right in with a case study which you can find on our website. In this video, the aim is to design an erbium-doped fiber amplifier to boost the signal from around 100 microwatts to at least 100 milliwatts. The challenge is that signal is at 1580 nanometers. This is far from the gain maximum, around 1530 nanometers. Let's see what can be done. For this simulation, we use the power form titled Fiber Amplifier for Continuous Wave Signals. We activate the first signal, set its power to 100 microwatts and wavelength to 1580 nanometers as planned. Since we don't expect a strictly monochromatic signal, we choose a super-Gaussian shape 5 nanometers wide and simulate the signal with 11 channels. Next, we set up the amplifier itself. We activate the first stage, select the fiber from our list of commercially available options and set the length to 2.5 meters. This should be long enough to absorb all the pump light. After setting some numerical parameters, we move on to configuring the pump. For optimal absorption in the erbium-doped fiber, we choose to pump at 980 nanometers with a 3 nanometer width and simulated with 5 channels. We simulate pumping in the backward direction, initially with 150 milliwatts. Of course, we want the simulation to consider amplified spontaneous emission, in short ASE, as this will significantly impact the amplification this far from the gain maximum. We also need to set the ASE wavelength range to ensure it covers a significant portion of the spectrum. Now we are ready to run the simulation. Let's inspect the outputs of our amplifier stage. We have amplified our 100 microwatt signal to only about 6 milliwatts, which is far from our 100 milliwatt goal. Most of our pump has been absorbed, with less than 10 milliwatts residual. But interestingly, we've produced a significant amount of ASE in both directions. Let's examine some output diagrams. First, let's look at how the powers of the signal, pump, and ASE evolve along the fiber, as well as the ASE spectra, with a special interest in the gain spectrum. The overview given by the diagram powers versus position shows the pump being absorbed, the signal being amplified, along with the forward and backward ASE. Here we see quite clearly how the ASE is amplified more than the signal. Now let's examine the ASE spectra to understand why this is happening. Essentially, the problem is that strong ASE results from high gain around 1530 to 1560 nanometers. This is substantially higher than the signal gain at 1580. Let's try optimize our design. First, let's use one of our parameter variation diagrams to see what would happen if we were to change the length of the fiber. A surprising observation is that a 6 meter fiber length works substantially better than 2.5 meters, although 2.5 meters are fully sufficient for efficient pump absorption. Let's see what's happening inside. Although the pump power is already largely absorbed by the middle of the fiber, there is still substantial erbium excitation and significant amplification in the left half. But why? The reason is that the backward ASE is reabsorbed and acts as pump light on the left-hand side for the longer wavelength signal, providing extra signal gain in the longer fiber. But since even the optimal length only produces around 22 milliwatts, let's systematically increase the pump power and continue to optimize the length. As you can see, we were able to achieve our goal of 100 milliwatt signal output. but this required a fiber length of 8 meters and a pump power of 1 watt. This is highly inefficient, with around half of the pump power being converted into ASE rather than signal power. So even though we have a solution, it's quite unsatisfactory. Let's try something different. In the power form, we can easily add a second amplifier stage, and then add a bandpass filter between the stages in order to suppress the ASE. The second stage is only 2.5 meters long and is pumped with 200 milliwatts. We of course consider ASE in this stage as well. Now, the first stage is shortened to 2.5 meters and the pump turned down to only 30 milliwatts. We also need to remember to pass ASE to the second stage. Finally, we add the bandpass filter, causing a wavelength dependent loss at the output of the first stage. Let's run the simulation and see what we get. And there we go. We achieve our 100 milliwatt output signal. But what about ASE? In the first stage, we still get more ASE than signal. But in the second stage, after the ASE from the first stage is filtered out, we see that much more of the pump power is used for signal amplification rather than ASE. This leaves us with a 5 meter long amplifier and using only 230 milliwatts of pump power, rather than the 8 meter 1 watt solution we had before. It's a much more elegant and efficient solution. I hope you've seen today how easy it is to run through multiple design iterations with RP fiber power. We tried designs with different lengths and even a 2-stage approach. Imagine trying this through trial and error in a lab. With these simulations, we ended up not only with a far improved design, but a better understanding of the amplifier itself. To learn more about what our software can do for you, visit our website and click on the software tab. For more case studies like these, click on the case studies and tutorial button under the encyclopedia tab. Thanks for watching, and please feel free to reach out with any questions.